this video, I'm going to talk about 5.3.1 part 2. In this video, we're going to cover a lot of very, I would say, abstract concepts, include Fermi sphere. We're also going to be deriving for the quantum degeneracy pressure, which we'll see later. But I hope you guys have, if you're here, I hope you guys have watched my previous video where I have found these expressions for these for the wave function for a electron in a free electron in a box. So I hope you watched my previous video. If you have not, I guess it's fine, because in this video there will be a lot more new concepts, which does not necessarily rely on part 1, but it will be good to know. So to begin with, we need to imagine a 3D grid. So that's why I have a picture here, because it helps you to imagine it better. So imagine you have a 3D sphere. So you have this is the z-axis, this is the y-axis, this is the x-axis. So I'm just drawing this, right? And for each axis, the values. So for kx axis, the value is going to be pi over lx, 2 pi over lx, 3 pi over lx, and blah, 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 blah. So what that means is that on the x-axis, there's going to be grids. And the distance between grids is going to be the same. So there's going to be a grid. And each of these grids, the value for the length of this grid is going to be pi over pi over line x. So it's going to go for the same for ky and kz. So you got to expand the same on this, same on this, same on this, and then you got to draw the grid on kz2, and each with the length of pi over l whatever. Like for example, for z will be pi over lz, for y will be pi over ly, you know. So once you have done that and you kept expanding the grid, and if you connect them together, you get this image I have on the left right here, right? Like you start in the center somewhere, and then let's say each of these represents a kx with a length of pi over lx. Each of this represents a ky with a length of pi over ly, and then each of these represents some kz with pi over lz. So that's what's happening here. And each intersecting point in this grid corresponds to a distant quantum states, right? Because for this, you can have many different grids, because once you have connected all the dots, you can have a grids here, grids here. Like for example, text will already draw this image for you. Like these dark spots are grids that represents a distant quantum state, because when you have a three-dimensional, when you're in the three-dimensional, right, y, x, I mean z, x, and y, right? Like any point on the three-dimensional could have its own unique, what do you call it, grid, if you were to connect everything, right? And it expands infinitely mathematically outwards. And it's just that in this case, each of these grids needs to have a length. For example, for x, it'll be pi over lx, right? So that's the only limitation. So that is what the text was drawing here, is that we have these on, we have the 3 axes, and on each of these axes we have segments, and then each of the length is either be pi over lx, pi over ly, pi over lz, depends on what axis you're choosing. So they have segments, and if you connect all the segments together, you connect all these dots, you get these intersection points. In this case, these intersection points all correspond to distinct quantum states. So now I'm going to ask you, what is the volume occupied by each state in this whatever space we created? Let's call this space K space. So this whole space we'll call it K space, right? So what is the volume? Well, we know that changing kx is pi over Lx, changing ky is pi over Ly, changing kz is pi over Lz. So therefore, a volume of a single quantum state in k space is you just multiply kx, ky, kz, right? Similar to how if you have a volume of a 3D rectangular solid, right? Like the volume will be width times height times length times width times height, right? Is what we're doing here. So this is going to give us pi over Lx, pi over Ly, pi over Lz. So this is going to give us pi to the power 3 over Lx, Ly, Lz. So this is the volume of a single quantum state in k space. So that's what this is. Or we could write this as changing kx, changing ky, changing kz is equal to simply pi q over v. So we write that as volume. So the interpretation is that each block in this k space we have here corresponds to a single stationary state of a particle, right? So each one of these volumes formed by different grids represent a distinct quantum states. So that's what it represents. So each of these shaded volume is one block, and there is one state for every block. So you can see if you just keep expanding this in terms of the x, y, and z axis, you have like an infinite amount of different blocks, right, formed by these intersection points. So what are we going to do with this information? So now is going to be the hard part, because we're going to talk about a concept which is called a Fermi sphere. So we know this system has a total volume. So the total volume is Lx, Ly, Lz, right? So suppose the system contains n atoms. So you have n atoms in the system, and each atoms contribute to some number d free electrons. So each atom contributes to d free electrons, and this typically can be 1, 2, or 3, this d. So we have a system that contains n atoms, and then each one of these atoms contribute d free electrons. And since, very importantly, that electrons are fermion and they obey the Pauli exclusion principle, which says that only 2 electrons can occupy a single quantum state. So that's very important in our case, because if each one of these shaded blocks contains some finite value, and this finite volume is the the quantum state, then it means that within this finite volume we could only have at most 2 electrons because of the Pauli exclusion principle, right? One with spin up, one with spin down. That's the most we can have in each individual volume that we can form from these. And there's like an infinite amount of volume you can form from this mathematically as you spread out more and more along the x, y, z axis. So at most 2 electrons in one of these finite shaded volume, and each one of these finite shaded volume represent the quantum states. So I think I talked about this concept multiple times in my previous video, so you should be familiar with it. So now I want you to imagine, instead of all the electrons occupying the lowest energy states, because that's what boson would do, electron fills k space starting from origin and extending outward. They occupy 1 octant of a sphere in k space. So what does that mean? What is an octant of the sphere? So I have an image here that would be very helpful. So let's drag this up. This is from the textbook too. This is what 1 octant look like. this is one octet. In this case, we only have one octet because, well, there are multiple octets to the sphere, but in reality, our k, z, x, y are all positive numbers. So they only occupy one octet of the sphere due to our positive kx, ky, kz. And when we call this, we call the radius of the sphere to be kf. So the radius is kf, which is what we call a Fermi wave vector. So what does this has anything to do with anything? So what we're trying to do is that, like, how I would imagine this is that I would imagine in your head you're trying to incorporate the image I have here with the octane I have here. So imagine in your head that these grids really exist, and among these grids we take only one octane of the spheres. Imagine all the you know, like all the grids already exist here, and each forming their own volumes, and we're looking at one octane because of the x, kx, ky, and kz being only positive numbers. So the volume of a Fermi of the Fermi sphere in K space is, well, the volume of one octane of a sphere mathematically is given by 1/8 times 3/4. So volume pi r cubed. In this case, our r is the Fermi wave vector. So in our case, the radius is going to be kf. So this is going to be pi kf cubed. Is what's going on here. And we know that each quantum state occupies a volume in K space of pi cube over v, right? This is what we derived earlier. This is how much volume each of these quantum states shaded block occupies in our space. And then this is our Fermi sphere that we have and the volume of it. So you, like, to get a more intuitive sense of what's going on, you sort of need to imagine the grids laying out in your head with all the shaded block, and on top of that you have an octane that has some certain volume. Then what you will know is that if you want to figure out the number of states, so let's write. So the number of, if I used to ask you to figure out the number of states in this case, it's going to be, well, the volume of the Fermi sphere. So this is the volume of this octane divided by how many quantum states we have within our Fermi sphere, right? So divide by volume per state in K space. So the total number of states is going to be, well, for the Fermi sphere, the volume is 1/8 times 4/3 pi kf cube over pi cube v is the calculation we have here. And this is going to give us the number of states that we have within our Fermi sphere, right? So this so this is the number of states within Fermi sphere. And if I found the number of states, so by the way, this is gonna simplify to v over 6 pi squared times kf cubed. So if I already found the number of states within our so-called defined Fermi sphere, which is one octane of a sphere, then if I were to ask you how many electrons are there in our Fermi sphere, well, since each state can maximum holds 2 electrons, right? So we only need to multiply the number of states by 2, because 2 is the maximum amount of number of electron a state can hold. So number of electrons, so Ne is just going to be 2 times V over 6 pi squared times kf cubed. So this is the number of states, and this is how many electrons we have in one state due to Pauli exclusion principle. So the total number of electron is given by a formula that says n times d, where n is the number of atoms and d is the number of free electrons contributed per atom. Like if we have 2 atoms and they each contribute 3 free electrons, right? Then our n is going to be 2, our d is going to be 3. So 2 times 3 is 6. So that makes sense, because if 2 atoms they each contribute 3, the net total you have for the number of electrons is going to be 6, right? So n times d is the other formula. So now what we can do is we can equate these two formulas. So n times d is just going to be equal to 2 times v over 6 pi squared times kf cubed is what we have here. And if we isolate our kf cubed, it's going to be 3 pi squared n dv. And if we use the formula for electron density, which is P is equal to nd over v, right? We substitute this, we can use this, and then we can simplify this formula, right? Because then ndv just becomes p. So k cube f is simply equal to 3 pi square p, or kf is equal to 3 pi square p 1 over 3. So this is the formula for the radius of our Fermi sphere, and then it's dependent on the electron density within the volume. So the energy at this Fermi sphere, at the surface of this Fermi sphere, is called something called the Fermi energy, and we can derive this. So we have kf is equal to 3 pi squared p to the power of 1 over 3, where p is equal to nd over v. And if you recall from my part 5 video, which is a long time ago, the total energy was meant to be a summation of x, y, z, correct? Because remember we broke the wave function down into 3 components of x, y, z. So if I flip all the way back up, see if I can find it. I think right here, this is the formula, and then kx squared plus ky squared plus kz squared here is just going to be equal to kf squared, right? So our energy formula we have for f is going to be h squared times kf squared over 2m. And if we substitute our kf in here, it's going to give us ef is equal to h squared over 2m 3 pi squared e 2 over 3 is what we have here for the energy. This is the energy at the surface of the Fermi sphere, and we can really look at the total energy of all electrons in the gas. So we can sum up the contribution of electrons at different energy level from k equal to 0 to k equal to kf. So looking back at our Fermi sphere, which is what we have here, if we want to find the contribution of electrons at different energy levels, so because this is the origin, right? This is the origin, which is k equal to 0, and then this Fermi sphere has some radius kf from k equal to 0 to k equal to f. Then we need to start using calculus. So how we're going to do this is that if you have 1 octane, so I'm just going to copy this image and paste it down here so it's more intuitively. So we can sort of draw on this a little bit to show what's going on. Is that we need to consider a thin spherical shell in the k space with thin shell with radius k, thickness dk. That goes along with the step of every calculus problem, right? Because if I want to use calculus on this 1 octane of a sphere shell right here, I need to sort of divide the sphere into infinite amount of thinner and thinner shell with different thickness. I'm not sure how should I draw this, but imagine expanding outward, like so the radius increases and then the volumes gets bigger, and then you can what's like an intuitive example? I don't think I can think of any, but you gotta let your calculus intuition kicks in here. Is that we need to, instead of thinking this as a 1 octane, we need to divide it into like infinite amount of thin shell, each with radius k and dk, so we can then integrate later to deal with this problem. So we have defined this thin shell, and the volume of the shell in the first octane is going to be 1/8 times 4 pi k squared dk, or simplify this as pi k squared dk over 2. And for the number of states in the shell, we need to do the same thing as what we did with the Fermi sphere volume, right? We need to divide the shell volume by volume per state, and the volume per state, remember, is pi squared over pi q over v, right? So the shell volume is going to be pi k squared dk over 2 divided by pi q over v. So this is going to be v over pi squared k squared dk. So this is going to give us the number of states within this thin shell that we have defined. And obviously the number of electrons is just going to be 2 times this, 2 times v over pi squared k squared dk. And the energy of each state is equal to h squared k squared over 2m. And something, so what we're going to do here is that when you consider the total energy, so D is going to be number of electron times energy per state, right? Because we're trying to calculate the total energy of all the electrons in the shell. It's going to be how many electrons you have and how much energy each electron or each state occupies, because the states can contain 2 electrons. So the total energy of all the electrons in the shell is number of electrons times energy per state. So we're going to get 2 times v pi squared k squared dk times h squared k squared 2m. So our d simplified is going to be h squared over 2m 2v pi squared k to the power of 4 dk. And we have dE here because we're looking at the total energy of an infinitely thin shell, right? Shell, just like how we have dk defined for the radius, to have an infinitely thin radius, if you like to call it that. Then each little section of this thin shell contains this amount of energy, and this is given by how many electrons you have within this thin shell, and how much energy each states carry in this thin shell. So we have more pages. More pages here. So we have D. Now is the very important part. Is that, remember that what we have been doing is that we have been cutting this Fermi sphere into thin shells, and we have been looking at the total energy of this thin shell. We've been looking at the radius of this thin shell, but overall, in the idea of calculus, you need to integrate because you need to sum up all the thin shell to obtain a full Fermi sphere, right? It's like when you calculate the area of a function that goes something like this, I don't know, and then what we have done is that we have cut this into, so this is dk and this contains some energy dE, but at the end of the day, to calculate the total amount of energy the sphere holds or something like that, we still need to integrate over the entire thing to figure it out, which is what we're doing here. So let's do it. So the E total, energy of the gas within our Fermi sphere, we're going to integrate from k equal to 0, because this is where we started, all the way to the radius of the sphere. That makes sense. So E total is going to be integrate from 0 to kf h squared over 2m 2v pi squared times k to the power 4 dk. And we just factor our constant, right? H squared 2m is the constant, v is also the constant, pi squared is also the constant. Yeah. So what we really get, I'm missing a 2v here. So what we really, no, this 2 actually just cancel out, right? So you just get h squared times v m times pi squared wait, did I do something wrong? So h squared over 2m times 2v pi squared times k to the power 4. So we remove all the constants. Okay. So I just rechecked my calculation and realized that at one point, I think back here, when I talk about the number of electron states in the shell, that is when I'm entering this step, this 2 in front of v never really existed, because back here we had a 1/2 term in front of this, so this is a 1/2 terms. I think when you calculate it all, when you multiply 2, I think it cancels it out. So I think during this step I forgot a 2 in here, which then will cancel out with the 2 we have here. So at this step, there will be no 2 in front of v, so it will be 2 h squared times v over 2m times pi squared is what we're going to have. And our integral is going to be 0 to kf and then k to the power 4 dk. This is a pretty easy integral to solve. This should be k to the power 5 over 5. So our E total is going to be h squared times v over 2m pi squared times k to the power 5 over 5. Or this can be written as the textbook, the way the textbook write it, which is h squared times v volume over 10 pi squared m times kf to the power 5 is what you get for the total energy of within the Fermi sphere. And we know that kp to the power 3 is equal to 3 pi squared times p, where p is the electron number density. Then we know that k5 is equal to k3 times 3 to the power 5. No, times 5 over 3. Then this is going to be equal to 3 pi squared times p to the power 5 over 3. It's going to be our k to the power 5th. So if we can further substitute this in, then the total energy is going to be h squared times v over 10 pi squared m 3 pi square 5 over 3 times p to the power of 5 over 3. And yeah, I think this is the way textbook wrote it too. Is you have this expression right here is what the textbook wrote too. So further down the textbook, we can further dive into this topic. We're going to talk about the topic of quantum mechanical pressure. So this sphere has some sort of energy, and this sphere also exerts some sort of pressure at the edge of the sphere, right? So if it exerts pressure, it does work. So if we want to figure out the work it does, how we're going to calculate that is that, well, first we need to look at how energy depends on volume. Let's scroll down. So from the earlier equation, the total energy we have is E total is equal to h squared over 10m times v times 3 pi square 5 over 3 times p 5 over 3. And by the way, I think there was no pi square here because it moved into it. So let's continue with this. This is the E total energy. And the P here again stands for the free electron density. So if we substitute P is equal to ND, so number of atoms times the free electrons over the volume into this equation, it's gonna give us, I think this is the final form that the textbook had. H bar square 10m times 3 pi square 5 over 3 times n to the power of 5 over 3 times d to the power of 5 over 3 times v to the power of negative 2 over 3. This is the final expression for our total energy of the Fermi sphere, and it depends on the volume. So to find out the pressure exerted by this sphere, we need to use calculus again. And you have to remember that for work in physics, the change in work is negative p times dv in this case, right? Because when you change the volume, you're doing work, right? That essentially is the definition. Like imagine you have a sphere and the volume change. Let's say the sphere expand, then it's doing some work by pushing it out. I'm not sure if and exerting some pressure also in that case. Try to intuitively understand that. Then we have the formula for this, which is, so for this, the change in the total energy with volume is dE total. So the change in total energy with volume is going to be partial E total over partial V times dV. Right? Because among all these variables within this E total formulas, we have a lot of constants, but the really only thing that matters here is the variable volume. So that's why we use partial here, because that is the only variable that concerns us, because E total is directly proportional to V to the power of negative 2 over 3, right? And then if you look at this total formula, if you treat everything else as constant, you only take partial of in terms of V, then you get negative 3 over 2 E total over V. v to the power of negative 2 over 3 minus 1, which is negative 5 over 3. So this is what you get. So after getting this, so let's write it down. So d total is going to be negative 2 over 3 e total over v to the power of negative 3 over 5 dv. So if we equate this formula to what we have here for dw is equal to negative p dv, then we can solve for p, which is p equal to negative d e total over dv, which is 2 over 3 times d total over dv. I think this is no over v. D total over v to the power of 5 over 3. So right now, if you substitute E total into this expression for pressure, what you really get is this whole thing over here, which is 2 over 3 times h bar squared times 2m, 10m times 3 pi squared 5 over 3 times n 5 over 3 times d 5 over 3 and v to the power of 5 over 3 too. Simplify this, this is v h bar squared over 5m 3 pi squared 5 over 3 times p 5 over 3 is what we have here. And this is really the quantum pressure. And the physical interpretation of this P is, this is the pressure arises from Pauli exclusion principle, which prevents electron from occupying the same quantum states, right? It's the reason why, like, for example, I've used this example in my previous video, which is an example of a neutron star. Is that when the gravity keeps collapsing and pulling everything towards each other, then eventually at some point you bring all these electrons together into such an enclosed space, right? Then at one point all these electrons gonna get squeezed, and you know from Pauli exclusion principle that they're prohibited from occupying the same state, right? So the result of that is that there's going to be this degeneracy pressure coming from the arises from the Pauli exclusion principle that actually fight against gravity. And if the gravity eventually gets strong enough, it turns the star into a black hole. So this pressure is what resists the compression of electron into the same quantum states. So if you were theoretically speaking, if you were to have an experimental machine that's able to do that, then if you try to attempt to squeeze 2 electrons into the same quantum state, there is going to be this quantum pressure, which we also call the degeneracy pressure, that fight against whatever force you're trying to pull them together. So that is what this formula is about. This stands for the quantum pressure, which is a pretty big insight in the physics community, right? And this is just a stabilizing internal pressure that has nothing to do with repulsion, which we completely ignored, and thermal motion, which we have also excluded. So this pressure is strictly quantum mechanicals and derives ultimately from the anti-symmetricalization requirement for the wave function of identical fermion. So that is, I think, all that is to this 5.3.1, and I hope you learned something through this video if you managed to last long enough to come through at the end of this, because it is indeed not a very easy topic. But I hope you have learned something from my new videos, and if you have any questions, feel free to comment down. And now see you in the next video.